Okay, now we continue with an extension of the standard PCA, which is a linear technology, to a nonlinear one, which is called kernel PCA, so it makes a nonlinear mapping. And just as a refresh here, what is a kernel? What is a kernel function? Often we use actually projections into higher dimensional spaces to better represent the data. For example, this could be a kernel function which increases now the dimensionality from a two-dimensional space into a three-dimensional one. Here this must be a 3, sorry. Right? Probably you can correct that. It takes feature 1, feature 2, and then the length both in square. So this is a higher dimensional representation of our data. So it blows up normally, a kernel blows up the dimensionality. And the kernel trick can always be applied when we have in some method, in some learner, actually the appearance of a scalar product between vectors, between feature vectors. Then the kernel trick is then such that we say, okay, we can represent that scalar product, the dot product, in a higher dimensional space by transforming these features using, for example, this kernel function into a higher dimensional space and calculating there actually the scalar product. That's called the kernel trick. And the kernel can be also seen as a matrix which is evaluated at each pair of feature vectors that we have. So it's also here p-dimensional. This is called the kernel vector. And using such a kernel trick, we can construct different nonlinear versions of the linear PCA. Let's look how this works. These are different kernels as examples. They are quite similar to the ones that we've seen in the Gaussian processes. We have also their kernel functions which define actually the covariance matrix of this infinitely dimensional covariance matrix. Here, for example, we have the radial basis function with an exponential kernel, with a linear kernel, tangents hyperbolicus, or this linear kernel here. This is a polynomial kernel with a power p. So these functions transform normally our, let's say, linear spaces into highly nonlinear spaces. For example, here it's like generating new features, like the polynomial features you probably know with regression. When we have a curve fit, we would do a linear regression. When we want to have a polynomial regression, we generate features which are all combinations of the powers of x. X squared, third power, x1 squared, x2, and so on. Is, for example, such a polynomial kernel, which is used for polynomial fit. Now, it can be shown, and I just do it really very quickly, that actually when we transform our feature vectors by these kernel functions here into these even higher dimensional space, we also get an eigenvalue problem. An eigenvalue problem which now isn't formulated in terms of the covariance matrix, but in terms of the kernel matrix. So what you do actually in kernel PCA is you do an eigenvalue decomposition of this matrix here, the kernel matrix, where all the entries of this kernel matrix are the pairwise entries for all feature vectors here. Xi, xj, which is the ij entry of this kernel matrix. And the explanation is given here for the interested reader here, how it can be done. It's just an explanation how we get to the eigenvalue equation for the kernel PCA. The most important thing is, I try to explain it like this. If we have actually this eigenvalue decomposition, C, and this is an eigenvector V, times lambda, and it turns out that we can represent our eigenvector V as function of our projected vectors here, of our transformed vectors using the kernel function phi, or the transformation phi. And then this is the original eigenvalue problem. C is the covariance matrix times an eigenvector V is lambda times V. This is just a representation of this V. It's just developed in this new space with some coordinate values alpha. It's a new space, probably even higher dimensional. Yeah? It's a representation of our eigenvector Vj. If we go further then, actually, we do the trick and say this is just a scalar. Let's take this out, and we formulate it like this. And this is now a matrix. This gives a matrix, and it turns out it's actually the definition of the scalar product. Phi, T, Phi, that's the scalar product. That's represented by the kernel matrix. So by this trick, now taking alpha out, we get this equation, CV is lambda V, and we have in here this kernel matrix. Now we multiply by another one, xk transposed here. And then you can show actually that what exists here is again a kernel matrix here. And then we have kernel matrix transposed. The coefficients in our high dimensional space, the other kernel matrix is lambda times again the kernel matrix. And then, okay, with these indices it's not that funny to play, but it turns out that this is just k squared. K squared times alpha is lambda times k. This is what turns out here. K squared times alpha j, these are the coefficients of the eigenvector j in this new space, is lambda times k. I take the factor k out, matrix multiplication, k times this, and it turns out, okay, at the same way we had an eigenvector, eigenvalue problem for the covariance matrix. After transforming it using a transformation function phi into a higher dimensional space, we get again an eigenvalue decomposition now here actually in this kernel space. And that's what the kernel PCA does. It makes the transformation, solves this eigenvalue problem, and then reconstructs, for example, that's the projected x then into this lower dimensional space, because Vj has a representation in this phi space, this alpha j. We can calculate by a multiplication of these alpha coefficients, given a kernel matrix where now the x vector, the full vector, turns in, and I multiply it out, I get the projected vector in my lower dimensional space. So what we need actually is to calculate here the kernel matrix for a given k, for a given x, and these are the solution of this eigenvalue problem. So we make a transformation, solve the eigenvalue problem here using the kernel matrix. These are the coefficients for the representation of the original data, and multiplying them times the kernel matrix here projects the data back into a lower dimensional space. That's how the thing is then represented as a nonlinear map. That's the kernel trick. The main thing you should take here with you is actually the kernel trick is always formulated like this. It's a representation of a scalar product. And whenever a scalar product turns out between feature vectors, actually you can apply the kernel trick. And the nice thing here is that it results again in an eigenvalue problem. And so there's not much more that you have to calculate. It's the same thing. You can efficiently solve these problems, and you can choose an appropriate kernel given the problem you have. Yeah? That's your expert know-how to select actually these mapping functions. But these projections now can map nonlinear transformations. Okay, that's kernel PCA. Now we go for methods which use similarity, which don't have the full feature vector actually available, for example, but just distance information between points in a very high dimensional space. What does distance mean? We also have to talk about that. What is distance actually? Yeah, distance can be defined in many ways. Here, I put it here an x in your slide. It's probably a y. Normally, I use the x for the high dimensional space and the y for the lower dimensional space. So that I'm consistent, please write here an x. And in the lower dimensional space, we would use the y, which are the projected data. So the goal of all these manifold techniques is actually that we represent only the distance matrix, not the full vector spaces, but we say if we have a distance matrix in very high dimensional space, I can just also calculate a distance matrix in a lower dimensional space and say, okay, let's project it to a lower dimensional space such that the distances between the data points are the same. That's the idea, keeping the distance information constant, so that the separation even in a lower dimensional space is the same. It's not always possible, but it's quite a good approach. Just to say, I want to represent my distance matrix in a lower dimensional space such that the distances are the same. And there are now different methods how to do that. Multi-dimensional scaling, local linear embedded, the name already says it, it's only a local embedding. This one is a global one, tries to match the global data set actually to a lower space, and the other one does it only on local subspaces here. ISOMAP does it even smarter. It calculates the distances not just as a Euclidean distance along the space, but it tries to make a graph of the structure of the manifold. So it would creep along this S and say the distance from this point here to the next one is not that one. This would be the Euclidean distance here, but it is this distance. This is called actually the graph distance. The question is how to construct this graph, which goes and creeps along the manifold in this lower dimensional space. That's the technique which is called ISOMAP. It looks for the geodesic distance, it's called. The geodesic or the graph distance. And this one would be the Euclidean distance. Of course, if you say, I want to keep this distance, it would wrap it together, but ISOMAP says, I want to keep this distance as long as it is here, in this higher dimensional space. And then t-SNE is a different one. It is a stochastic technology. It tries to map the whole thing, the higher dimensional probability distribution using a lower dimensionality distribution. Okay. The summary here, I think this slide is quite important. It summarizes the most important part if you want to ever use dimensionality reduction technologies. Multi-dimensional scaling, once, just in short, keeps the distances as they are in the high dimensional space, and it's a global method to do that. Local linear embedding only keeps local distances similar. Means they just look in a neighborhood of a given data point and says, in this range, I want to represent the distance matrix as similarly as possible to the original distance matrix. It makes it locally for each point. ISOMAP makes this creeping along the graph of the data, and this one reduces the dimensionality by trying to keep close distances close and big distances distant, using actually a probabilistic approach. We'll see here. And LDA, don't want to touch this. You can also just make a scratch over here. It's another technique. We don't look at it today. LDA. Good. What is similarity? Here we would say, okay, what is the distance between these two pictures? There's some similarity, of course. We would say, okay, probably the hair here. Hair is quite similar, the eyes or so. But in a mathematical sense, similarity is always described by a matrix. And now, what is a matrix? It's a mathematical thing which is defined by these four axioms. A matrix is a distance measure, and this distance measure is always positive to night, so it's bigger or equal to 0. If it is 0, it must be the same data point. The next thing is it is symmetric. Well, if I measure the distance from A to B, it must be the same like from B to A. And then we have the triangular inequality, which also must hold as a force axiom. That's actually the distance measure. Now, how it is defined, we can think of a lot of distances here. The most important one is actually the Euclidean distance, or the LP norm, which is normally written like that, with double words, and index P means if P is 2, it's the Euclidean norm, it's just the square of all the components and the square root over it. If P is 1, this is just the absolute value and the sum of it, the L1 norm. But there are other distances. There are graph distances, for example here, by this S curve. There's a Wasserstein metric between two probability distributions, so you can compare very different things using a matrix. If you have to say what is close, you have to define an adequate matrix. If two probability distributions should be close, we will see, we will take the matrix of the Kullback-Leibler divergence, which tries to fit two probability distributions as close as possible. The most important are here. The LP metric, normally P is 2, the square of all components squared and the square root. If we put P to infinity, this same norm tends to emphasize only the maximum value of it. So we can show, or you can show, one can show actually that the L infinity norm is just the maximum coefficient of a vector. It turns out that only the maximum survives if we let P go to infinity. So this is the maximum norm. And the L1 metric, probably you remember Rich and Losser regression, where we had this L1 and 2 norm, the same norms here. Right? It's just the sum of all absolute values of the coefficients. There are other metrics, just as example, for example, the Helling distance, how to compare two strings with each other, how similar is one word to another, now just in terms of strings. And here are some metrics which are valid, for example, for text data. Also, like you've seen in the Google video here, actually similarity of words can be defined in many ways. For example, by the neighborhood they have, what are the accompanying words or so. But we could also just look at the letters itself and say, how far is kitten from Sydney? How distant are these two words? And we can also define metrics there and reduce the data using these metrics. It's just an outlook that you have to think about distances as a general concept, a very general concept which describes similarity in any data space. And depending on the data you have, you can define your own metrics to define similarities. And these similarities are used to define distances. And these distances are used to reduce the data. Because similar data can be compacted to one cluster and another one to one cluster. So I need less representative data to represent that. Okay, what does MDS do? It seeks for a low-dimensional representation of the data where these distances are as similar as they were in the high-dimensional space. And it tries to do it globally. So this is a global optimization problem for all data points at once. The process doing that is quite complicated, but I just want to point out here that's actually what is optimized. The distance in the high dimensional space minus the distance here in the low dimensional space, this should be as close as possible. That's the loss function we want to minimize. And then we find the representation of this xy. How does this scalar product have to look like in this lower dimensional space such that this loss function is minimized? This is actually the optimization problem which is formulated for MDS. The main thing is actually we want to keep the distances in the high dimensional space as close as in the lower dimensional space to this. An algorithm like this goes, I have sketched it out here, it's quite complicated. We don't have the covariance matrix, we only have the distance matrix, and the distance matrix square is something like the covariance matrix. And using this after a centering operation, it leads again to an eigenvalue problem, where we can use it then to represent the lower dimensional data. So what is calculated later, this is actually the solution of this optimization problem. This is this algorithm. But we will just experimentally look at it, how it works in detail. For you, important to know is it's a global method. It's a manifold method here, which keeps similar distance similar in the lower dimensions. For example, here such a thing would then be projected correctly into, for example, a two-dimensional space. It's a Swiss roll, which is then unrolled with the letters of Swiss. Okay, only distances are used. It's just linear algebra, that's why it's quite fast, and tries to preserve the global distances between all pairs of data points. And now comes the difference to local linear embedding. This only wants to keep distances similar in a local environment around the data point. And if we take here Euclidean distances, classical MDS is actually equivalent to TCM. There's no difference, but we can change the metrics if we want. Okay, what is local linear embedding? This is now the second technology, actually. And the idea here is that we reconstruct. The idea is that I try to plot it here. Actually, if we have a data space like for example this S, let's make it like this. This is now the manifold. Then actually local linear embedding tries to, in a local coordinate system, represent this data such that the weights for the representation of the data are the same also in this lower dimensional space, which is, for example, then flat and two-dimensional. So if we have actually here V1 and V2, this is preserved also here. Let's look at it. And then these are kind of partially overlapping subspaces where locally actually these weights are conserved. That's the idea. And we project it here to such a patchwork of small subspaces actually, which are continuously over the data points distributed into a lower dimensional space. But the idea is to conserve actually here. The idea, for example, here, if I look locally like an ant, if I am an ant which travels along this S, I would say actually my space is locally flat. So I represent it by a two-dimensional plane. So my dimensionality would be 2, and I just calculate the transformation matrix to make this hyperplane local. And I will make here a patch like this, here a patch like that, like that, like that. And later I just unfold it onto a two-dimensional flat. So I project this one to this one to this one to this. That's the idea of local linear embedding. And the algorithm is quite complicated again. It's just for those who want to know exactly how this works. But it tries now to keep this local representation in this local subspace, which is this local hyperplane, which goes along this S, keeps these distances. It tries to represent the data points by other data points in the neighborhood, and it wants to keep these weights constant also in the new space, in the lower dimensional space. That's it. Okay. Here I have a picture. You select one point, this would be the x time. I select k neighbors of it, and using the coordinates of these k neighbors, I want to represent the full hyperplane at this space, fit it in there. This gives some values for v, and this VE shall be conserved in this lower dimensional space. And the lower dimensional space is such, actually, that the representation locally is the same. So I can use the same coefficients for the representation of the big X in the higher dimensional space and the Y in the lower dimensional space. That's the main idea. And how to calculate is again quite complicated here. It's written here. And I've also put on the Moodle an overview from Martin, which gives a nice overview about this dimensionality reduction technologies. Not going into the details here like the others, but just saying LDS makes this in globally, the other one makes this, what's the difference, and so it's quite a good idea to look at this paper, at least for the methods we have discussed. Okay. ISOMAP, the third method of this manifold methods, is now the following. I've explained it already. It tries actually that they have this manifold, it tries to construct this manifold explicitly as a graph structure. So actually, if I have the data points in here, it tries to unfold this S as a graph structure, like this. And this graph can just be flattened out in 2 dimensions, but the distances are then measured along this graph, and not in the high dimensional space. And ISOMAP tries to keep this geodesic distance constant between data points in the lower dimensional space and the higher dimensional space. So it must first construct a graph of the data along this hyperspace, along this manifold, and then calculates all the distances along the graph. This is called a geodesic distance or a graph distance. And here it's again shown, and especially if I have rack data like that, this data set is called Swiss roll, it's a cake, it's like this roulade. You can generate this also in scikit-learn. Actually, a linear method would say the distance between here and here is very important because it's close, and I want to keep them close. ISOMAP says, no, these points are not really close, because I got an idea about the internal structure of the data when I constructed the graph of these data. And on the graph, these distance points, or these 2 points, are very distant to each other. So ISOMAP tries to separate them, while, for example, PCI tries to bring them close together. Or NDS as well. And here is a more complicated graph. It would go along, actually, like on a Google Maps, along the streets, and not just taking the plane going crossover. That's what ISOMAP does. And now we come, what is the disadvantages actually? K must be quite high. Number of neighbors or so. We have 2 parameters, K or epsilon here. That we don't have any shortcuts along this S here, but we really have to avoid such a shortcut here. We have to select quite a big K. This could also happen when generating the graph. And these are hyperparameters we have to set here. The neighborhood radius and this K. And these parameters you have to try out. You really have to fiddle a bit with it to get good representations of the data. Now the last method is t-SNE. It's a manifold learning algorithms which is now based on matching not only distances but probability distributions. That's a stochastic approach. And it tries to keep close points as close as possible and far points as far as possible. And the main thing is actually that we say, okay, the data comes from a probability distribution P, which could be a multivariate distribution, We want to represent now the data by a lower dimensional multivariate distribution Q. This is also a way to reduce dimensionality. Let's say this is 700 dimensional. This is only 40 dimensional, but still we want to make them as close as possible. How can we do that? Now we match not distances, but we match the probability distributions such that they are as close as possible. Now we have to define a distance measure between 2 probability distributions. When are 2 probability distributions similar to each other? And what you take here is actually the Kullback-Leibler divergence. We'll just see what this is. Also here we have parameters, hyperparameters that we have to set. One is the perplexity, which says that how loosely to pay attention between local and global aspects. How do we weight local things or global things? So it's a tuning parameter that we have to set on our own. If you click on that link, you'll find quite a nice demonstration of t-SNE, how it works. It's online, it runs in your browser, and you see how this works a little bit, and you can play with these hyperparameters like the perplexity, for example, and see what happens. It's quite complex. I think nobody can really predict what happens first. It's just experience and looking at it. So it's a lot of representation of the data. Okay, why is it called actually t-SNE? T comes from the student T distribution, because the normal distribution decays a little bit too fast. And they have experienced and say, we just have to take actually a distribution which has a longer tail, because these long-term correlations play an important role, so that we are able to represent also distant points correctly. So they take the T distribution. It works in two steps. We first calculate the probability distribution between these 2 points. So what is the probability that I find point I given point J? It's also a neighborhood thing. It could be a Gaussian neighborhood, for example, that we say it is exponentially less probable that I find this point if it's distant away. We make an estimate of this one for all pairs of neighboring points. The step 2 is then we try to recreate that probability distribution in a lower dimensional space, where now I and J actually are representations of the data, which are lower dimensional. So a Y, Yi and a Yj, which only have, for example, 5 dimensions. But we still can calculate the probability distribution. And then we make them as close as possible, as similar as possible. And how do we do it? By minimizing that point here. This is the Kullback-Leiber divergence, which tries to match a probability distribution P to a probability distribution Q. And you can actually understand it as a kind of a weighted sum of the logarithm, the difference of the logarithms of these 2 probability distributions. If they're very close, if they're very similar actually, this would be 1, so the logarithm is 0, and then it's very low. So we want to minimize it. Then they are more similar to each other. And that's what's done actually in the t-SNE approach. This is the high dimensional representation. It's calculated by the xi, xj. This is calculated by the low dimensional yi and yj. And we try to fit those, and at the end actually find the y's actually given this equation to say they should match as close as possible. What I've shown here is just the same thing, not with the t distribution, but with the normal distribution. The t distribution actually can be approximated by this exponential Gaussian distribution. This would be actually the probability of finding I given j. And we would just say, yeah, it's a normal distribution. If I'm close, the probability is very high that I find another one, which is quite similar. If I'm far away, the probability decays like the bell-shaped curve from Gauss. This one is the same. Now I didn't put any variance, and I didn't put any mean and offset or so. I just say this is now a low-dimensional representation of this probability between 2 points in a lower dimensional space where we have the y's. And the goal is to find these y's. And we do it by matching these 2 probabilities over this equation. This is actually what t-SNE does. So not directly on the singularities, on the distance measures, but on a probability distribution, which is again actually represented here by a distance in a lower dimensional space. So not the distance directly, But the distance goes in as actually the leading parameter of the probability distribution. So it's mapped to a probability. Now we try to match two probabilities with each other. Okay. So we've seen different methods. t-SNE is quite powerful, you will see. t-SNE will manage actually to separate out the MNIST data set in the exercises that follow now. The others won't be able to do that, but it's also difficult to handle. But the main important thing is actually PCA we can directly do on the data. It's linear, we can invert the process, we can turn it around. Then we have manifold methods. MDS acts globally, tries to keep the distances similar. Then we have local linear embedding here, tries to have the local distances similar, only local. The isomap measures the distances along a graph that is constructed along the manifold. And then we have t-SNE, uses the distances, but at the end compares probability distributions and tries to match it. That is mainly the message I want to give you, that you have an overview of these methods, the main actually approaches that can be taken for dimensionality reduction. And I think these four methods, they show all a little bit different things. One like local, global, linear, non-linear. One goes on the distances, one on the data set itself, and the others on probability distributions. These questions we will also answer in the exercises. These are really practical questions from Aurélien Gérard. It's quite a practical book from him. And now, a last thing here, which we do not touch, but you should know, probably also you know, probably you've heard of autoencoders, actually. And the PCA is a kind of an autoencoder, because what is an autoencoder? It's actually here, it's shown as a fully connected 5-layer network, where we generate in the middle a bottleneck with only few weight parameters, which means actually we have a data representation here with only few weights. Means we reduce the dimensionality here, it would be 784 to let's say 40 nodes in the middle. This is automatically reducing the data set's dimension using here a bottleneck in a neural network. And by doing this, now, how do you teach an autoencoder? You say you have to generate the same output as the input. And this is easy to train. The input should be generated by the output. So I teach it. And then we will find the best sparse representation of the data by the weights in the middle. So, and what is called here is an encoder. If I want to construct really compact features, I let it run until here. If I want to generate numbers out of these features, I let it run from here to here. It's a really powerful method. Neural nets, autoencoder networks, where you just force actually the dimensionality of the weights of a middle layer to be very, very low. Not too low, otherwise you'll not be able to reconstruct the data anymore, but to a limit where you say, okay, this is the right measure, this is the right dimensionality of these weights. So if at the same time, training an autoencoder gives you the encoder. In PCA, this would be the projection to the low-dimensional data, and the decoder would be the transformation using the transformed matrix UT. This is U in PCA, this is UT. Yeah?
Why do we have to add noise to the image?
I think here you just generate noise, for example, to make it more robust. It's a data augmentation technology. So that you shape actually, especially with images, it's common that you say, okay, let's, for example, shift the data, let's turn it a little bit, let's change the gray values, the gamma values, let's add noise to make it more robust. So you can add, because samples are normally quite expensive, you can generate augmented data using the same data by a factor of 5. This is easily done. And it makes, actually, it avoids overfitting as well, and makes the network generalize better. It's better for generalization. Or what you can also say, you can use it, if you have a noisy image, you will use this as a noise filter, because you will construct them as a labeled function near the real image. And it filters out noise automatically. This is the second advantage, that we can use data reduction actually to filter out noise, because noise is quite uncorrelated. It is not represented by one of these principal axes, and then you can filter these axes out. These are unimportant, uncorrelated information, and you get it out by PCA. This is also what we'll do in the workshop now, in the lab. Just add noise to the images and reconstruct these noisy images after reducing its dimension. And then we see, okay, we will get more or less noise-free images, because this noise is differently distributed over the day. Yeah, that's more or less it for today. That's the summary of today. We have seen, okay, the most important thing is certainly PCA. You should be able to explain how PCA works. What is the meaning of the eigenvalue? Why do we need the eigenvectors? What do they mean, and so on? You should know that PCA can be employed in a nonlinear way using the kernel trick, and you should know that the kernel trick is such that you normally represent a dot product by a kernel matrix. You can always use it, for example, also for support vector machines, the kernel support vectors, and so on. You should know these advantages. This is the main thing, actually, why we do it. We can save time and storage space by actually compressing data. We can filter noise. We can remove multicollinearity. For linear problems, this is a problem, because if I want to fit actually a hyperplane in an n-dimensional space, and I have two columns which are the same, a linear method cannot decide which vector is now more important. It assigns these values randomly. But after applying a PCA, you will consider this dimension is the same. It will flip it together. It will project it onto the same vector. So it will automatically fall out. And so it's a way using PCA to avoid multicollinearity in linear problems. Because they show in the design direction, it will be only represented, this direction will be only represented by the same eigenvectors. So it will be projected on the same one. Visualizing is an important thing when we want to learn from data. We don't know before what kind of information in this data. Then often actually dimensionality reduction technologies are just used for visualization processes. And it makes actually many learners much more robust, because actually we reduce the dimensionality of the features. Means also that we have less parameters that we have to estimate to fit. Okay. Are there any questions to dimensionality reduction techniques? Have you ever heard before of dimensionality reduction, or is it the first time that you hear that? Never heard before, no? Okay, it's a very nice thing. It's data compression. The opposite thing, the inverse thing, is also very important. How do you generate from a floor plan a three-dimensional building? This can also be generated automatically today. It's not a topic here. So both ways are quite important. But here we look now at the data reduction. Okay, good. Then let's make a break before we start. That's what will we say? 3:10, okay?